Hi, welcome to my video on proofs with trapezoids or trapeziums. Proofs with trapezoids. Definition of a trapezoid: a quadrilateral with exactly one pair of parallel sides. So let's draw a trapezoid. It has exactly one pair of parallel sides. So notice if I have A, B, C, D, then I'm making AB parallel to CD, and we have a trapezoid. And as a result, A, B, and D, C are the bases of the trapezoid. Angle A, angle B, angle C, and angle D are the base angles, and AD and BC are the legs. So the legs are not the parallel sides of the trapezoid. Also, let's look at the definition of a right trapezoid. A trapezoid with exactly one pair of parallel sides and one of its angles 90 degrees. So if I draw and make this a 90, and I extend this, so I have one right angle. So notice these two sides. Let's call it P, Q, R, S. Notice that PQ is parallel to RS, and we have a right angle at S. And since we have a right angle at S, we also have a right angle at P. So these are two. If a line is perpendicular to one parallel line, is also perpendicular to the other. So this, if there's a right angle at S, there has to be a right angle at P. So this is a right trapezoid. And again, the bases are PQ and SR. The legs are PS and QR, and the legs, this is a leg, and this is a leg, and this is a base. I'm going to just call it B1 and B2. Bases are the parallel sides, and the legs are the non-parallel sides. We also have what we call an isosceles trapezoid. It's a quadrilateral with exactly one pair of parallel sides, and the legs are equal. So if I branch that out and extend that over, this is an isosceles trapezoid. Notice I have the two parallel sides. Let's call it F, H, V, and a G. Notice that FH and GV are parallel sides, and to be an isosceles trapezoid, the two legs have to be equal. So that's an isosceles trapezoid. Again, only one pair of parallel sides. These two sides are not parallel, because if we had both pairs of sides parallel, then we would have a parallelogram or a rectangle or a rhombus or a square. But if you go with exactly one pair, then you have we call it trapezoid. And let's look at the perpendicular. This is the perpendicular symbol. The perpendicular distances between any 2 points on the parallel lines are equal. In other words, if we have two lines and we make the two lines parallel to each other, so if I do a perpendicular distance, so if that's perpendicular, so let's call this A and B. Oops, make it A and B, not A and A. Let's make this line A and this line B. So if this segment is perpendicular to B, it must be perpendicular to A. Hence, if we draw another segment perpendicular to B, then that segment must be perpendicular to A. And if I draw another one perpendicular to A, it must be perpendicular to B. So that means if this is an X or Y, and this is an H, T, and this is a D and an F, then X, Y is equal to H, T equals to DF. The perpendicular distance between parallel lines are all equal. So let's turn over and look at some proofs with the trapezoids and proof. But before we do that, let's prove what we did on the previous page. Let's prove that the perpendicular distance between any 2 points on the parallel lines are equal. The perpendicular distance between any 2 points on the parallel lines. So first of all, let's make 2 lines parallel to each other. So here we have 2 lines, and I'm going to make them parallel to each other. And let's draw a line perpendicular to both of these. So let's call this A, B. And let's draw another one and call it C, D. And we also make them perpendicular. So let's prove that these two distances are equal. So we're given that, let's call this line M, and let's call this line M. We're given that M is parallel to N, and we're given that AB is perpendicular to DB, and we're given that AD is perpendicular to BD. And as you can see, they're perpendicular also to AC. And we're going to prove that AD equals CD. So the parallel lines and the perpendicular distances are equal. So how do we go about it? Well, let's take all the givens. I'm going to write down, there's all those givens. I'm going to save time in doing the proofs. All these givens are written down in here. And number 2, we have to prove, now we have these perpendicular here and here. So if we establish the fact that we got perpendiculars here, so let's look at that AB is perpendicular to AC, and CD is perpendicular to AC, and if a segment is perpendicular to one parallel line, then is perpendicular to the other. Okay, we have the perpendiculars done. Now we notice that because they're perpendicular, that means that angle B, angle D, angle A, and angle C are right angles. And that's because definition of perpendicular lines or segments. Because if we have the lines perpendicular, which we do here and here, here and here, that means that all these angles are right angles. That means that A, C, D, B is a rectangle. And that's definition of a rectangle, which means that we have all 90-degree angles, 4 90-degree angles. And since we have a rectangle, that means that AB is equal to CD because of opposite sides of a rectangle are equal. And that's the proof for saying that the perpendicular distance between any 2 points on the parallel lines are equal. So these, if you have 2 parallel lines and you have perpendicular distances between them, then these distances are always equal. So the perpendicular distance is at a right angle. So let's have a look at some more proofs. prove the base angles of an isosceles trapezoid are equal. The base angles of an isosceles trapezoid are equal. So let's draw an isosceles trapezoid. Base angles of an isosceles trapezoid equal. So we're given that E, let's name it E, F, H, T. E, F, H, T is an isosceles. I'm going to use trapezoid, TRAP, abbreviation, is an isosceles trapezoid. So, an isosceles trapezoid, but we're saying that EF is parallel to TH because we have an isosceles trapezoid. And we're saying it's isosceles, so that means that ET is going to equal FH because an isosceles trapezoid has the two legs equal. So these two legs are going to be equal, and these are going to be the parallel sides. So we have to prove that the base angles, so we're going to prove angle T is equal to angle H, and we're going to prove that angle E is equal to angle F. These are the base angles. So let's begin the proof. So let's put all the givens, and again to save time, all these givens, we're writing them in here. So I'm going to save time by not having to write all these out because the video is going to be long enough as it is. And number 2, all these givens are written in. So what I now have to do is draw a perpendicular from E down to TH, and I'm going to say it intersects at A. I'm also going to draw a perpendicular from F to TH and intersect at B. So that's a construction. So I'm going to draw EA and FB such that EA is perpendicular to TH and FB is perpendicular to TH. So that's the construction. I'm allowed to draw a segment from E perpendicular to TH and from F perpendicular to TH. That's the construction. Constructing the perpendicular lines. So as a result, we have that if these are perpendicular, that means that EA is equal to FB because the perpendicular distances between parallel segments or lines are equal. That's the proof that we just did. So now we have this segment equals this one. So we can either say that because these are perpendicular here, we can say that these two angles are going to be equal. But if we do make this angle at A equal to the angle at B, then the triangle is going to be an ASS. So we can't have an ASS in proofs. So instead of saying let's put 1 right here and 2 right here. So let's say that angle 1 and angle 2 are right angles. Definition of perpendicular lines or segments. That means that we have the triangle EAF and the triangle FBH are right triangles. Because we have right angles of right triangles, that's the definition of a right triangle. And because we have right triangles, now we can say those two triangles are congruent. So triangle FBH are congruent by hypotenuse leg congruency. Notice that this is the right angle, this is the hypotenuse, and this is the leg. So because the hypotenuse is the leg of this triangle is equal to the hypotenuse and the leg of this triangle, these two triangles are congruent. And again, ET is hypotenuse because it's opposite the right angle. FH is hypotenuse because it's opposite the right angle. And that means that we have angle T equals angle H. CP, congruent parts of congruent, CPCT, congruent parts of congruent triangles, congruent. Now we need to get the other angles, but because I've drawn these perpendiculars here, then I have the angle E and the angle F. Now there's two more angles at there. There's three angles. TEF has the big angle and the two small ones. So let's continue. Because these are parallel lines, that means that angle T is supplementary to angle TEF, and angle H is supplementary to angle HFE. So this angle right here is supplementary to TEF, and this angle H is supplementary to HFE, and that's because the interior angles, that's supplementary, that's the PLT, parallel line theorem, and the alternate interior angles are supplementary, PLT. And as a result, we have angle H equals angle T. That means that angle TEF is equal to angle HFE by supplement angle theorem. Supplements of congruent angles are congruent. We did that in the proof on congruent triangles. So now we have remember that's angle E went before, and that's angle F. So this is angle E, this is angle F before I drew the two perpendiculars here. So we proved that both pairs of base angles are equal in an isosceles trapezoid. Remember, an isosceles trapezoid has the legs equal. So now that in an isosceles trapezoid, all the base angles are equal. And we have another proof to do, but this time is practice. And practice means pause the video and see if you can work the proof out. Prove the diagonals of an isosceles trapezoid are equal. So, if you had to do this proof from scratch, you would draw an isosceles trapezoid. So let's go with A, B, C, D. So let's say that A, B, C, D is isosceles and trapezoid for short, and we're going to make these two parallel to each other because a trapezoid has only two pairs of parallel sides, and we're going to make that AD is equal to BC because they're the legs are equal, and we're going to prove that the diagonals, so we have to draw the diagonal and draw this diagonal. So hopefully I can draw it pretty good. There they are. So we have to prove that AC is equal to DB. The diagonals are equal. So again, let's take, this is the given. So all these givens, we can put them in right here. There they are. I'm just saving time. So all those givens, ABC is an isosceles trapezoid. The lines are parallel, and these segments are equal are written in right here. So number 2. Now, based on this, we can have, I'm going to separate them now. I'm going to show you down right here. And I'm going to draw this one. So this is A, D, C, and this is B, C, D. So I'm separating these two triangles to show you that these are the diagonals AD and BD, AC and BD, AC and BD, but the triangles are overlapping, so I'm drawing them down here. So what we have is that we have AD is equal to BC, and we have their parallel sides, and the diagonals are, we have, this is a common side, and we have, just then we proved, and you can, we proved that this angle here and this angle are equal. So in this triangle, ADC and BCD, these are the base angles, so they're equal. So notice I'm separating them here so you can see it. Now you can see that I have two triangles congruent by SAS, and therefore AC is equal to BD. So I'm doing it down here because this is overlapping. So now I'm going to fill that in. So we got a given. So we can say that BC equals DC, common side, so that's in both of these triangles, right here and here. And number 3, and because it's overlapping, I have to go angle ADC is equal to angle BCD. So that's angle D is right here. This is the angle C, which is here, but I had to use 3 letters because it's overlapping here. And that's the base, we just proved that, base angles of an isosceles trapezoid are equal. And as a result, we now have the two triangles are congruent. And the triangles are ADC, ADC, as you can see here, and BCD. Or we can say B, go this way on this one, but I look down here, and there, look, as you can see, side, angle, side, side, angle, side. Congruency. And number 5 is that AC is equal to BD. CPCTC, corresponding parts of congruent triangles congruent. So that's another proof done. Hopefully these proofs are making sense, and we have another one to do. The more we do, hopefully the more we'll understand, because proofs are sometimes many students find them difficult. And practice means pause the video and excuse me, and work this proof out. Draw out a diagram and see if we can do the proof before I do. Here we go. We have this figure, and we're given that PQRS is an isosceles trapezoid. We have PQ parallel to SR, and we have angle T is equal to angle Q. And we want to prove that PT is equal to QR. So how are we going to prove that? So we look it over and we say, how can we get these two sides? Well, because we have an isosceles trapezoid, I can see the parallel sides, and now I can also see that PS is equal to QR. PS equals QR because of isosceles trapezoid definition. And how am I going to get, why did it give me these two angles? There must be angles related here. So I keep going, and I say I need to get, if I want PT equals PR, now that means I must have PT equal to PS, and PS equals QR. So if I can get these two equal, then I can do a transitive property. So I need to get PT equal to PS. So the parallel lines, I'm going to use some numbers. Let's use angle 1 and angle 2. Because of the parallel lines, 1 is going to equal to 2. Because I have an isosceles trapezoid, PQRS, 1 is equal to Q. So if 1 is equal to 2 and Q is equal to 2, that means 1 is equal to Q. But we also given that T is equal to Q. So put all them together and we'll come up with T is equal to 2 by transitive. And hence we'll have PT equals PS converse of ITT. And by transitive property, then we can say PT equals QR. So proof is a little bit, there's no congruent triangles here, so you have to look around getting angles equal. So here we go. Again, number 1, there's the given, save time, I just put them all in number 1. So we have PS equals QR. Definition of an isosceles trapezoid. Notice abbreviation for isosceles, abbreviation for trapezoid. Now we have angle 1 equals angle Q. Base angles of an isosceles trapezoid are equal. Now we have the parallel lines, so that means that angle 1 is equal to angle 2. PLT, alternate interior angles are equal. PLT. So because these lines are parallel, 1 is equal to 2 alternate interior. And we have, up here, I just read it in here, angle T is equal to angle Q, just so you can see it here. That's in the given. So if we have T is equal to Q, Q is equal to 1, 1 is equal to 2. So if we put all together, if 1 is equal to Q and 1 is equal to 2, that means P is equal to 2. And if, Q is equal to 2. So if Q is equal to 2 and Q is equal to T, that means 2 is equal to T. So angle T equals angle 2. And again, that's the transitive property, but there's more than one of them. So as I said, 1 equals Q, 1 equals 2. So that gives me angle Q equals angle 2. Because T is equal to Q and Q is equal to 2, T is equal to 2. So there's transitive property, but there's a few transitives, 2 or more. I say 2. Right, so we do these two here, that's one transitive. Do this one as another transitive, so there's 2 transitives. And number 6, that means that PT equals PS. If T is equal to Q, then these two sides are equal. So that's the converse of the ITT, converse of the isosceles triangle theorem. If 2 angles are equal in a triangle, then the sides opposite those angles are equal. So PT equals PQ. And again, we have PS equals QR and PT equals PS. That means that PT is equal to QR by transitive. And I'll put the 2 numbers in there now. That's it in number 2 and in number 6. And now in here I'm going to put 2. There's 2. I'm going to write TWO here. instead of saying 2, because the 2 could be referring to the statement. So there's 2 transitives. I put T, spell that out, TWO. So there's the proof for that theorem. And again, there's no congruent triangle, so we had to relate the angles to get to the sides equal. So we had to get these 2 angles equal to get these 2 sides equal, and then do a transitive. Now we have another idea going on with a trapezoid. The definition of a median. Well, let's draw a trapezoid. Here we are. A, B, C, D. And this is a trapezoid. And we have, now, if we pick up these 2 midpoints here, so if we call this a T and an H, so we have A, B, C, D is a trapezoid. And we have H and T are midpoints of the legs. So if we join these 2 midpoints, that means we made HT is a median. MED is a median of the trapezoid. So the median is a segment joining the 2 midpoints of the legs. And also the median, so that means that HT is also parallel to the bases, parallel. So HT is parallel to AB, and HT is parallel to DC. So the median is joining the 2 midpoints of the legs. Okay, now that we explain what a median of a trapezoid is, remember, this is in a median of a triangle. A median of a triangle, a median leaves here and goes to here. So if that is the midpoint, a median of a triangle is a segment drawn from a vertex to the midpoint of the opposite side. So AM is a median because this is the midpoint. M is the midpoint of, let's say this is BC. So this is a median of a triangle drawn from a vertex to the midpoint of the opposite side. But a median of a trapezoid is a segment joining the midpoints of the 2 legs. So let's do a proof. Prove the median of a trapezoid is half the sum of the 2 bases. So if we set up M, A, T, H, we set up X and Y are the 2 midpoints, and we join those 2, so that's the median. So we're given that M, A, T, H is a trapezoid. We're given that X and Y are the midpoints of MH and AT, which are the legs. And we want to show that the median is half the sum of the bases. So we want to show that the median, which is X, Y, is a half the sum of MA plus HT. Because there's the median, X, Y, and there's the bases are MA and HT, because the bases are the parallel sides of the trapezoid. So to do this proof, we need to draw this diagonal. And this diagonal, as it happens, is passing through this point O. And this point O, there's more proofs to be done, but I didn't do them, that if you draw a line from the midpoint parallel to the base, then this segment or line goes through the midpoint of this side. So we look at this triangle, AHT. If you draw a line or a segment from the midpoint of this side, AT, parallel to this base, then it'll pass through this midpoint of this side. So remember, AH is a diagonal, and this is the same here. This is a midpoint parallel to MA, therefore this O is the midpoint. So O is the midpoint of this diagonal, which is, as you can see, related to excuse me, the midline there. So let's have a look at the proof. So here's all the givens. Again, you can write them all out, or some of them, but let's save time. Now we got, because this is a midpoint, and this is the midpoint, let's take that XO is a half of MA. And also we have OY is a half, OY is a half of HT. So if you take this triangle right here, AHT, these are the two midpoints. So the segment joining the two midpoints is half this third side. These are the two midpoints in this triangle. So this segment is a half of this side here. So that's what we said. This is what we proved earlier on. It's called the midline theorem. The segment joining the two midpoints of the sides of a triangle. This is half this side and parallel to it. So as a result, we can go XO add on OY is equal to half of MA plus a half of HT. And that's the addition property of equality. We're adding the segments together. So what we have is that XO plus OY, XO plus OY is equal to XY. And that's the segment addition property. And hence, you can see XOOY is here and here. That means XY is a half of MA plus a half of HT by transitive. Again, the two of them are here. These two are here. So that means XY must equal these two. That means XY is a half of MA plus HT. And we did, that's the distributive property. That's the distributive property. Remember, just to review, distributive property is A times B plus C is equal to A, B plus AC. So we take a half. I took the half out by factoring, but we really call it the distributive property. So we're proving that the median of a trapezoid is equal to half the sum of the two bases. So we're going to do that down here. So we have M, let's call MED for median of a trapezoid. The median of a trapezoid is a half the sum of base 1 plus base 2. Something like an area, but not quite. So the median is half the sum of the two bases. So we have the median. So we're trying to find, let's just say that's the M there. The median, M, MED for median. I didn't want to use M alone because the M alone would have signified like a slope or things like that, midpoint, M standing for midpoint, but this is MED, median of a trapezoid. That's a half of B1, 10, B2, 16. So that's a half of 26. So the median is 13. And here we have the median is a half of, again, B1 plus B2. So the median, MED, is 17, half of 11 plus B2. If you multiply by 2, you get 34. 2 times a half is 1, so you get 11 plus B2. So B2 is 34 minus 11. So over here, B2 is equal to 23. So that works out the median of a trapezoid and some problems related to it. And here's a proof done on it. So that brings us to the end of the proofs on trapezoids. There are only some proofs. There are many more proofs to do on trapezoids. But the more proofs you do, hopefully the better you understand what you're doing. And if you like my video, click the like button, subscribe button, visit my math website, www.mathfullyexplained.com, to find more information about me, my videos, and the content. That's the content is on my YouTube channel called Math Fully Explained. Thank you for viewing my video. Bye-bye.